Okay, let's get back to the class. Can you still with me? Okay, very good. So we will go to the next subtopic, next design, the header, which is very important because when we look at the history of the header, it's quite interesting, or the reason why we have header. Just think about this. For example, we have a piece of hardware, a digital system or a circuit. So how we want the circuit to be able to perform calculation, all right, to do arithmetic, to calculate, all right. Right, we human can perform a calculation uh, very easily, right? Because we have a brain, so we can add a number. 1 plus 1 we get 2, 1 plus 2 we get 3, and so on and so forth. But for example, you are the engineer, right? Before the digital system was invented, right? So how can you imagine that how you want to create or want to uh, do calculation using a circuit, using a hardware, where the hardware is not a living thing, right? So it is quite interesting that we can create uh, a hardware that can do calculation, all right, where we give the number 1 plus 1 and we can get 2, and from that, all right, we can get an even bigger number. Okay, so it is quite interesting, right, that we can build a hardware that can calculate, can process a data. Okay, so that's uh, how the adder is come about. Yeah, and to design or to build an adder, we need to understand the addition process. And remember that in hardware, all right, the hardware cannot process or cannot add the number in just like a human do the calculation. All right, the hardware cannot do that. All right, for example, we give decimal 10 plus decimal 10, the hardware cannot do, all right, cannot perform the calculation. All right, this because the hardware cannot represent a decimal number. All right, so the hardware can represent a number in the binary format. All right, that is why we have binary system. All right, because we want to represent the number in hardware. All right, and what kind of hardware we use to represent the number? That hardware or device is a transistor. All right, because with transistor we can easily represent 0 or 1. All right, 1 represent transistor, or transistor on represent number 1, and transistor off represent number 0. All right, so if you have many transistor, you can represent a bigger number, right? For example, number 110, you have transistor on off off. All right, 1100 on off off. Okay, so with transistor we can represent a number, and also with transistor we can create the hardware that that is able to calculate. All right, that is adder. So we need to understand the concept of adding number in binary. All right, because the hardware perform calculation or perform addition in binary. Okay, so in binary, for example, we have a 1-bit system, the simplest system. For example, we have x and y. All right, x is 1 bit and y is 1 bit. So when we add this 1 bit and 1 bit, so you can have the result. Here we call it a sum. All right, sum, and here we call it carry. So for example, we plus number 0 and 1, you have your sum equal to 1 and your carry equal to 0. All right, but if you plus 1 and 1, you should have 0 for sum and 1 for your carry. All right, so you can have all the possibilities of x and y, 0, 0, 0, 1, 1, 0, and 1, 1. And you can have the output for all of the combinations. And from that, right, because you have combination of x and y, and you have the output, so from that you can get the equation. All right, so this is easily can be represented in a truth table. All right, so you have 0, 0, and this is 0 and 0. 0, 1, you have sum equal to 1, carry equal to 0, and so on. Okay, so from that you can have two output system, and this is clearly that represent an AND gate, right? Because only one combination you have 1, all right, which is 1, 1. For other combination you have 0. So this is clearly an AND gate. And for this one, all right, if 0, 0 and 1, 1, you have 0, and if the input is different, is not the same, I mean not the same, 0, 1 or 1, 0, you have 1. And this is clearly XOR gate. All right, so from that, you can have the circuit. And this we call a half adder. All right, and we can create the symbol for that. X and Y is input, are input, S and C are output. Okay, so we have the hardware that can calculate now. But the problem with half adder is that you cannot do this. You can only do 1-bit addition, X and Y. What if you have 2-bit addition? All right, so for example, number 10 plus 01. Not a good example. I give the example 11 01. This is a better example. So when you plus this to this, you have 0 and what? You have the carry to this bit, right? Which is 1 and 1, 0. All right, you have this carry. Okay, this cannot be implemented using half adder, because half adder with half adder you can only add this section. All right, 1 bit. So that's why you have a full adder. All right, where you can do addition for a number that more than 1 bit. For example, you have 5 bit in this case. All right, or more than 5 bit, any bits. All right, for example, this is X, this is Y, and X is 5 bit, Y is 5 bit also. So you add, right? So if you look at this, yeah, you can see that you have another bit, another signal, all right, for every addition, which is the carry in, all right. So means that a good adder should have another signal, which is the carry in signal. In the case of this addition, produce a carry, all right, so that we can add to the next bit, all right. So this 3 bit is added together, and you can get the sum, and the next here, all right, is the carry, all right. This one is carry from the previous addition, all right, and this is carry for the next addition. Okay, so if the previous addition don't have any carry, so this C in equal to 0, all right. But if the previous addition has carry, so this carry will be 1 C in, all right. So a good adder should have 3 input, all right. Carry in the number that you want to add, and the output is again 2, sum and the carry out, right? So again, to create the circuit for this, you can create the truth table, all right. So this is the truth table for the full adder. So because we have 3 input now, so if you have 3 input, so you will have 8 possible combination from 0, 0, 0 to 1, 1, 1. And this is the output for carry out, and this is the output for sum. All right, so let's, for example, 0 plus 0 plus 1. So you have 0 plus 0 plus 0. So you have sum equal to 0 and carry equal to 0, of course, because all are 0. But if you have 0, 0, 1, means that you plus 0 plus 0 plus 1. So your sum equal to 1 and carry equal to 0. But if you have 0 plus 1 plus 1, so sum equal to 0 and carry equal to 1. All right. And if all are 1, you have sum equal to 1 and carry equal to 1, for example. And from this, you can have your equation from the K-map. All right. So you simplify the equation. You can have S sum is actually X XOR Y XOR C in XOR C, and carry out is actually X and Y or X and C or Y and C. All right. So now we have the equation. To create the circuit is very easy, right? So you can have your schematic, yeah, and this is your equation. And to model using Verilog is very straightforward. You can use data flow modeling because you have this already, all right, and this. Okay, so this is how you model your full adder. Okay, so you have how many input? You have C input, A, B, or X, Y in our case just now. This one we have a new circuit. So if I draw this circuit, it should be looks like this. Okay, you have A input, you have B input, and you have C I input, and you also have S output, and another output is CO. Alright, so that's why you have a port list like this, and this is full adder, name it FA maybe, oh no, full adder, not FA, so the name must be the same as that one. So this is named as full ADD, full add. Right. So input is of course CI, A and B, output S and CO, and you can use data flow modeling. Assign S equal to A XOR B XOR C in CI, and assign CO equal to this or this or this. Right. So you have the full adder. Okay. So, but the interesting part is that you can do this, right? You can use your 1-bit full adder to create a bigger adder. For example, you want to create a 2-bit adder, 3-bit, 4-bit, 10-bit, 100-bit. You can do that. All right. So if we connect like this, this is exactly the same as what we have done in manual calculation. All right, for example, this plus this plus this, the output is this, and the carry is go to the next part. Yeah, so in this case, we can write like this: x1, x0, y1, y0. All right, when you add this, you can has s0 this. All right, and the C, the carry is here, C1. So C1 should be here, and you add again, you have S1, and of course this is for X2, Y2, and you have S2, and the carry from this is C2. All right, and so on. Okay, so the concept from manual calculation we can actually implement in hardware. All right, by doing this we can have a bigger circuit. All right, so this is how we create a 4-bit adder using hierarchical design methodology. And of course, when you use hierarchical design methodology, you need to have use the module instantiation. Yeah, and this is of course structural modeling. Right. So how we do that? Full adder. All right, we call this module. All right, in the bigger module. So in this bigger module, we can actually this. Yeah. So I want to draw this somewhere here so that you can see the connection. Maybe I remove this one and try to draw from this. So we want to do this. Okay, we have one adder, another adder. Actually, we have 4, but I just put it 2. Okay, 3. Okay, so we have A here. A is 4-bit now. Yeah, B is 4-bit now. So this should be B0 and A0. This, oops, sorry, A0, B0, and the output should be S0. The input here is CI, and the output is C1 here. The next one is B1, A1. The output is S1, and here should be C2, and this one is A2, B2, right? And we should have this one is S2, and the last one will be okay. I just use this space so that you can see this. This should be A3, this should be B3, and this should be C3, and the output here should be S3, and this is C1, C2, C3 only. There's no output in this case. No, CO. In this case, the name is CO. Okay. Alright, so now let's move this here. Okay, you can see. So now this, our 4-bit adder 4, the name is adder 4. So the input is CI, so should represent this one, A and B. So we have A and B here are A and B, and A and B is not 1-bit but 4-bit. A is 4-bit, B is 4-bit, S, these are S, and again S is 4-bit, and CO is only 1-bit. All right. Input here, input CI is 1-bit, so this is how we declare a 1-bit input CI, and this is A and B, and A and B are 4-bit. All right, 3 to 0. So A3, A1, A2, A1, A0, same as B, B3, B2, B1, and B0. Output as 3-bit, 4-bit, as 3 to as 0, and output, this one is 1-bit, CO, 1-bit, and you have internal wire here, 1, 2, 3, C1, C2, and C3 are internal wire. So this is this wire must be declared as wire. Okay, wire 3 to 1 C. So you have C1, C2, and C3. Now, how to instantiate this 1-bit adder to this a 4-bit adder? So again, you need to call the name for your 1-bit adder, which is full add. In this case, you name it as add 0 here. So the first here, all right, the first signal here, what is the first signal here? The first signal here must be this. I need to Okay. So the first signal here must be, look at this, CI. Alright, CI. So must be, in this case, CI. So this CI is actually CI. Alright, so that's why you have CI. And the second one is A. Alright. So in this case, you A for this you connect to A0, and B for this you connect to B0. Alright. And S for this you connect to S0, and CO for this one you connect to C1. So if I can draw what is the signal from the previous module, so this in the previous module, in this module is named as CI, this is S, this is CO, this is A, and this is B. Alright, same as this one. So the first module is done. What about the next? The next, same module, alright, same module. The name is now ADD1, and the CI for the second module is connect to not here. This is CI. CI is connect to C1. That's why you have C1 here. And A is connect to A1. That's why you have A1. B is connect to B1, and S is connect to S1, and C out is connect to C2. That's why you have C2 here. Done. The third one, C, all right, CI is connect to C2, A2, B2, S2, and C3. Done for the third one. And the last one is C3 is the input, connect to CI in this case, right? A3, B3, A3, B3, S3, and the output for the last module is CO, right? Then you have all the connection and module, right? So by doing this, you will now have the 4-bit adder. All right. When you have another one, you can have a 5-bit, 6-bit, or any bits that you want. All right. So this is why hierarchical modeling design methodology is very important, right? So you can reuse, always reuse your design to create a bigger design. All right. And this is how design engineer, how we design a complicated circuit. All right. So you you know that the microprocessor, for example, all right. So the technologies, or people always say that the microprocessor has billion of transistor, all right, means that billion of gate, all right. So in this case, one adder, how many gate you have? 1-bit adder, you have 1, 2, 3, 4, 5 gate, all right. So 2-bit adder, which is the same circuit actually, all right, you have 10 gate already, 10 gate. So 4-bit adder, you have 20 gates already, all right. This is 4-bit adder, which is quite small, right? For nowadays, we have 64-bit already, 64-bit or 1 to 8-bit already in the ALU, right? So that is the adder alone, right? So for multiplier, for example, later on you can see multiplier, you will use many adder to build the multiplier. So the size is quite big. So that's why we have a very big circuit, millions of gates. But actually, from that million or billion of gates, you design or you reuse your previous design, a smaller design that can be managed. All right. Okay. So that is adder. Now, what if we want to sub a number? All right. Want to do how to do subtraction? All right. The add is, yes, easy. Now, how if we want to do the subtraction? We want to sub 2 minus 1, for example. How to do that in hardware? Okay. Do, um, do we need to use the same concept as designing an adder? Means that we have the Boolean equation and the truth table and the circuit. The answer is difficult. All right, because the sub will involve borrow. All right, for example, you sub a bigger number from a small number. All right, so you need to borrow. All right, and to implement borrow in hardware is not that easy. All right, so subtract is a little bit tricky. All right, but it's still possible. All right, by using the binary system. Right, now the trick is that in what we call the sign number. Sign number. So what is sign number? Sign number is how we represent negative number in binary, in digital. All right. How we write -1 in binary, for example. So to do that, we need to use the sign number, and you have learned this in your undergraduate program, maybe, right? For example, this we call sign and magnitude number, right? So there are many ways to represent sign number or negative number in binary. One of them is sign and amplitude, right? So means that if this is your binary number, an n-bit binary number, b0 to bn minus 1, and the MSB, most significant bit, is representing the sign. So for if MSB is equal to 0, means that the number is positive, and if MSB is equal to 1, means that the number is negative. All right, and the simplest sign representation in binary is this, to use sign and magnitude. Means that if we want to represent -5, for example, and our system is 4-bit system, yeah. So the +5 in 4-bit system is 0, means that positive, this is MSB. 101, this is +5. Okay, so in sign and magnitude representation, -5 is just negative, represent negative, and the magnitude, which is 101. All right, this is -5. And if negative 6 is 1, 110 is 6. Negative 1 is 1, 0, 0, 1. Alright. So this is the simplest representation of negative number. But this number cannot be used. The problem is this number cannot be used in hardware calculation. Alright. Means that no meaning in hardware calculation. You cannot use this to do adding or subtraction. Alright. Now come to the next number or next kind of representation, which we call complement representation. Alright. So the first complement representation is what we call the first complement representation. So what is first complement representation? First complement representation is just like this. When we want to represent number negative 5, for example, all right, so we change to binary 5, change to binary 4 bit, which is 0 1 0 1, right? And you complement each bit, you have 1 0 1 0. Okay, so this is first complement number, right? And the definition is this. All right, k equal to 2 power of n minus 1 minus p. K is the number that you want to find. N is the size of your number, your system. All right, so for example, let's say we want to find minus 5, right? So we want to find k in first complement representation. All right, so equal to should be, and our n is 4 bit. Yeah, 4 bit. Sorry, this is not 4 bit. N is equal to 4. Okay, 4 bit. So means that 2 power of n, you have 2 power of 4, you have 16 minus 1 minus p. P is the magnitude of your number, which is number 5. So what you have? You have 10, right? You have 10. So that's why you have 1010, which is 10. Okay. But the simplest way is to complement each bit. All right. So you have 1010. Okay. Now let's look at this. First complement addition, because we see this, yeah. Minus 5 now we can represent as 10 10, correct? Now let's, for example, we want to do this 6 minus 5. We want to do subtraction. Okay, so because we don't have subtractor circuit, we don't have. So what if we write the equation like this? 6 plus, because we have adder, minus 5, and we have minus 5 number, which is 1010. Okay, now we can use adder to do subtract. All right, by doing this. So 6, you can have 0 110 in binary 4 bit. All right, and you use adder 1010. this is 5, sorry, this is 6, and this is minus 5. And you add. What do you have? You have 0 plus 0, you have 0. 1 plus 1, you have 0, and you have carry, which is 1. And you have 0, and you have 1 carry, and you have 0, and you have 1, right? And this carry, if you bring to this, you add again, you plus, you have what? 0, 0, 0, 1. Look at the answer here. 6 minus 5 equal to 1. And you have 1. Meaning that by using first complement representation, we can do subtraction. We can sub. Yeah, we can subtract. So this is good. Meaning that we can do subtract using an adder. So let's look at this. Yeah, look at this. This example. So again, when we want to plus, yes, no problem. Just plus. So 5 plus 2, you have 7. 5 in binary plus 2, you have 7. No problem. Alright. Look at this. 5 minus 2. Now we want to implement 5 minus 2. Where we can do this. 5 plus minus 2. But you can use adder. Alright. So this is 5. This is minus 2 in first complement representation. Alright. And of course this is adder. So because 2 in 4-bit is 0, 0, 1, 0. So when you complement, you have 1, 1, 0, 1. That's why you have this. Okay. So when you add, you see, you get this and this carry, you bring to here, you add again, you have 3. Yes, of course, 5 minus 2 is equal to 3. And same as this one. Minus 5, this is minus 5, minus 2, you add together, you have minus 7, and this is minus 7, yeah, because when you complement this, you have 1, 0, 1, 1, 1. So this is 7. And this is negative, negative 7. Correct? So, means that if you use first complement number, now we can do the sub. Yeah, we can subtract a number without designing a subtractor actually. Alright. So we can use an adder to create a subtractor. Alright. But the problem here is with first complement number is that you need to add 2 times and you need to check whether you have the carry or not. Alright, means that the carry that is more than 4-bit, yeah. So this is your system is 4-bit, so the bit number 5 here you need to add again. So you need to add or you need to add 2 times. Alright. So that is the problem with first complement. But we have another number system, we call it second complement representation or two's complement representation. So what is two's complement representation? So this is a definition. So for example, again, we want to represent minus 5. Alright. So our number is 4-bit system. So in this case, we want to find k minus 5 for second complement number. So 2 power of n is 16. This is k1 is first complement. This is this is second complement. Yeah. Don't confuse not this one. This one, yeah. This one. This is first complement. So 16 minus the p, the magnitude of this, which is 5. So you have 11. And 11 in binary is 1 0 1 1 for 4-bit system. Okay, so means that to get second complement is actually you complement the number and you plus with 1, because when you want to get first complement for minus 5, you have number 5, you complement, all right, you have first complement, and when you add with 1, you have 1 0 1 1, which is exactly this one. You have the second complement, all right. And the good thing is that when you use second complement in your addition, you can have something like this. For example, when you add positive number, it's okay. It's straightforward. For example, 5 plus 2, you have 7. Okay, straightforward. But when you want to do subtraction, again, plus 5, you want to minus 2. 5 minus 2. So this is actually 5 plus minus 2. You can use adder. Alright, and minus 2 is now, we use second complement to represent minus 2. So this is 5. This is minus 2. Alright, 1 1 1 0. So minus 2, for example, so you have 2, 1 0, you complement, which is 1 1 0 1, you plus 1, you will have 0 1 1 1, exactly this one. So this is minus 2, minus 2. So you add together. So 1 0, you have 1 0 1, you have 1 1 1, you have 0, and you have 1 carry, and you add, you have 0 and you have 1 carry, and by ignoring this one, you have the result already 3 without the need of adding this like this. You need to add again. Means that for first complement, yeah, first complement, you need to add 2 times to get the result. But by using second complement, you add 1 time and you get the result already. All right. This is why we learn second complement in binary. All right. If you don't know why you need to learn first complement, second complement, this is why. All right. Because we want to subtract, and subtract in hardware is not that easy to build. So we manipulate the number to have first complement and second complement. And for your knowledge, first complement is no use in computer. So in the computer system nowadays, the number system that we use is second complement. All right. So in digital design, in computer design, in digital system design, the number that represent negative number is the second complement number, instead of first complement or sign and magnitude. All right. Hope you're clear on that. Okay. All right. Any questions? So I saw in the chat. The result says, can I zoom out the page? Is it too small for you? I think this is full view already, full page already. Can you see this clearly? I'm sorry. I think this is full page already. Can you see this clearly?
Yeah, doctor.
Yeah, I think this is big enough. So, any question regarding this?
Thank you, doctor. Thank you.
Yeah, I hope you get the idea. Yeah, why we need to learn first complement, why you need to learn second complement. Yeah, because we want to implement subtraction in hardware. All right, and the one that we use is second complement. That's why we don't have third complement or driver complement. All right, second complement is enough. All right. Okay, so if not, so maybe another 10 minutes. Now, how to design the subtractor. Okay, so the idea, we know the idea already. Okay. Right, because we know the idea already, so now how to implement in hardware. All right, quite straightforward. So let's say, for example, we have the 4-bit adder again. So let's, for example, this is our adder. Yeah. This is my adder. Okay, I have 4-bit adder like this. And the idea is that we want to do this. Okay, A minus B. All right. So remember, what we need to do is A plus minus B. Correct? So how to do plus? So do plus is easy. So we use full adder. Minus B. Okay, so now A can be straight away get fit to the adder. Let's say this one is A0, A1, A2, A3, and the output should be the same. As 0, S1, S2, S3, and here should be C in, no problem, C1, C2, C3, and C out maybe. Now this is S minus B. How to get minus B? So, and minus B here is the second complement. Correct? So the second complement, what we know is that we need to have, all right, for example, if this is B, P is 0, 0, 0, 0. So we need to have minus complement B, which is this 1 1 1 1, correct, and 1 0 is not a good example, sorry, not a good example. 1, B is 0 0 0 1, so we have 1 1 1 0, and you need to add 1, right? You need to add 1 plus 1 to get second complement, which is 1 1 1 1. So this is minus 1, right? So minus B, what you need to do is you need to complement the B, right? So how to complement the B? So if this is B3, yeah, if this is B3, so to complement is to use the NOT gate. So you get the complement. And to complement B2, you can use the NOT gate. You can have B2 bar. To complement B1, you can have the NOT gate here. And of course, for B0, you have the NOT gate. And you can get this one. So how to get plus 1? To get second complement? Very easy. You have this. See? You just set this C into 1, means that you plus 1 to B0 and A. So you get complement value of B. So if you have, you plus, yeah, you plus, add with the complement number of B, right? Then S is the result of A minus B. Okay, so this is the subtractor. So you see, from adder you can get subtractor with a little tweak. All right. By using the second complement number. All right. So, any question? So if no question, we are 11:40 now. We will finish at 11:45. Now I want to give you assignment. Yes, the one that you're waiting for, right? Any question? No?
No.
No means good, either good or bad. Why I say that? No question means that you understand almost everything.
Sir,
Yeah.
I have question that's related to responses to the software. Actually, I downloaded the software and then it had no. When I also downloaded the devices, I couldn't like connect the device to the software. Could you show us how to do that?
What is the problem? Can I'm not clear.
Like I downloaded the software and then installed it on PC. And when I started it, like there are no devices that belong to everything. Literally no devices.
Oh, okay, okay.
And I sometimes again I downloaded the devices, but I could not like load them to the software. Like I don't know how.
All right, all right, all right, all right. I I mean, normally when we install the software, we will be asked by the software to install the device, yeah, and you need to have your device file ready, but you still should be able to install later on after you install the software. But I'm not sure what is the problem. Maybe we can discuss on that in, if you're free, uh, later, afternoon, or other times, so we can I mean, you can share your screen, all right, and let's me see what is the problem, what is the exact problem. Okay.
Okay, but how can I contact you afternoon, sir?
Yeah, you just,
Same WhatsApp group?
yeah, WhatsApp group.
Okay, okay, thank you, sir.
Okay. All right, so back to this. So for the assignment, the first assignment, I want you to do this. Yeah, this is called the adder subtractor circuit. Okay, so this adder subtractor circuit, do you, okay, can be used to add numbers or subtract numbers. All right, so it depends on this signal. So when this signal add sub signal, add has this bar, all right, means that it is activated when the signal is 0. So means that if this signal is 0, this circuit will perform the addition. When this signal is 1, this circuit will perform the subtraction. So for example, if I set this to 0, so the output here is equal to, because this is x and this is y, so the output here s is equal to x plus y. But if I set this value to 1, all right, so the output here will be equal to s equal to x minus y. All right, so this circuit can perform addition and subtraction at the same in the same circuit, by setting this signal to 0 or 1. If 0 is its add, if 1 is its sub. All right, so I want you to do this, all right, using a hierarchical design methodology. Means that you need to create a 1-bit full adder, all right, just like this one. Where is it? Yeah, like this. Okay, like this, and you use quarters to simulate the result. Yeah, I will post the complete question on Edmodo, so that you can refer to that question, and also you can submit your assignment, your report through Edmodo. It's easier for me to collect your report. Yeah. Okay. Hope you clear on that. So I think
Sir, like the submission of the assignment, like in author, there is no subject for your subject is not listed in the author for the UTHM author website.
not author, Edmodo. I will use Edmodo, or maybe author. Later I will set up, and we will communicate using WhatsApp. Yeah.
Okay,
Yeah. I will give the instruction through WhatsApp. Okay. So okay, so if no other question, so we will end our class here. We can continue next week to just a little bit more comparator, and the last one is the ALU or multiplier, and the ALU, and we will go to the sequential design, which is very interesting. Yeah. Okay. So thank you, everyone. See you next week.